sandwich theorem says. Suppose that I have a function, say I have the function f of x is equal to x squared plus 1. Everybody okay with that? Mm-hmm. And suppose I have another function g of x is equal to 1 minus x to the 4th. Okay. Is everybody okay with those two? Mm-hmm. All right. So then what I'm going to do is I'm going to graph those. And what does x squared plus 1 look like? Parabola that's shifted up 1 unit, okay? So as it's shifted up 1 unit, it looks like such. And then 1 minus x to the 4th, wouldn't you agree that looks very similar? It's just upside down, a little bit sharper. So I'll draw that like this. Are we okay with that? Mm-hmm. Then we're going to draw another function. We're going to call it h of x. And what we know about h of x is not a whole lot. The graph is very weird shaped. It doesn't have a nice shape to it like these do. But we know it always stays between the other two. It always stays exactly between the other two. Always between the other two. The question for us is very simple. What is the limit of h of x as x approaches 0? Does somebody want to guess what the limit of h of x is as x goes to 0? 1. It is 1. How are you so certain? Would you agree that the limit of this function is 1? Would you agree that this limit is 1? So if h of x always sits between those two, then therefore h of x must have the very same limit. Everybody agree? Do you see why they call it the sandwich theorem? Yeah. H of x sits between those two. It's a very, very important piece to be able to look at as we investigate this idea, which is the derivative of sine. We want to look at the derivative, and one way to write derivative is not to use that apostrophe, but to do d over dx. The derivative of sine of x, what does that look like? What is the derivative of sine? Okay, that's our goal to get through today. I'm able to walk in front of class basically every single day of the year without any notes, okay?
This is the one time you need them?
I have to have the notes. I can't remember all the notation and everything. So this is the one time I need it. Everything else I'm normally would just say, I remember it all. I don't remember all this. But I do know that in order to find the derivative of sine, we have the limit as h goes to 0. This is how we always prove a derivative. We did this when we set up the power rule. And we're going to have sine of x plus h minus sine of x all over h. Does that look familiar?
Yes.
Yeah, that's our formal definition. You did that on the test, right? Mm-hmm. Never going to have to use the formal definition again. You always get to use the power rule and other things. And so just the challenge is that not everything's written as a power, right? Like sine of x, there's no power there. Okay, it's not a polynomial. So what's the derivative? Well, we want to expand on this. Do you remember from your time in trigonometry last year? Do you remember when we did sine of angle A plus angle B, and we expanded that? Yeah. That was a trig identity that we used, and this is to try to heighten the fact that we're going to have to use some trig review. The sine of A plus B is equal to, if you remember, the sine of A times the cosine of B plus the cosine of A times the sine of B.
Last year we got that on the sheet for the test. Are we going to have to memorize this?
We'll talk about the things that you're going to have to memorize and things you won't. That is one you won't have to memorize, but there are a couple of trig functions that you will have to memorize. For example, please tell me you remember this one. Sine squared plus cosine squared is?
1.
1. Thank you. That one you have to know. That is of the greatest importance. You also know that tangent is equal to what over what? Sine over cosine. Those are ones that are absolutely essential. You will have to know those. Okay? And I have that sheet that you guys got last year. I printed that off for your review package, so you'll be able to reference that. So let's expand this out. We do have the limit as h goes to 0 of, and we're going to have what? We're going to expand this addition piece. What's it going to be? Sine of x times cosine of h plus cosine of x times sine of h minus sine of x all over h. Good. Everybody with me? Okay, we'll play around with that, and what we're going to do is we're going to separate some pieces, okay? We're going to gather the sine of x's together, so I'm going to do the limit as h goes to 0 of sine of x times the cosine of h, and then I'm going to gather this minus sine of x over, and that's all over h. Okay, what am I missing? This piece right here. So I'll have to add cosine of x times sine of h over h. Oh, I need to make it bigger. It's hard to see. Yeah, I got you. Okay. Whoop.
Your pen is here drawing.
Your pen. A little bit better?
Yeah, thank you.
Okay, yep. Okay, good. Oh, stop doing that. Go away, go away. Okay, all right, now we're almost there. We've got now the limit as h goes to 0 of, I'm going to factor out the sine of x. See how this has a sine of x that's shared in common? So we have the sine of x times whatever cosine of h minus 1 over h is. And then here I'm going to factor out the cosine of x. I get cosine of x times the sine of h over h. What's that, Lily?
I figured it out.
Okay. So the big question is, notice what, I have a variable h going to 0, right? So the question is, what is that limit? Because I end up with sine of x right here. So let's say that that limit was 2, then this would be 2 sine of x. Get my point? And let's say that this limit right here was 0, for example. Well, then that would just disappear, right? I mean, the big question is like, what is that limit and what is that limit? And those are tough limits to find. And there's sometimes, like the other day I sat down with Aiden and I showed him the proof of the product rule. I actually came up with that proof on my own. I'm pretty proud of it. But I didn't come up with this proof on my own. I have no idea how the person generated this and if it was Newton or who kind of did this. But it's rather impressive. And it takes us to an important picture that we're going to draw, okay? And so we're going to draw this picture over here. I actually drew the picture ahead of time on the whiteboard, but then the whiteboard restarted and the entire picture was now gone. You know what I mean? So I apologize. I had a better picture. We're going to do our best to get this picture drawn right here. And what I'm going to do is I'm going to draw the portion of a sector. The portion of a sector. So a sector is just part of a circle. Going to help you construct that. We might not get through this whole piece today. We've lost a little bit of time with our Friday fun, which I think is okay. But we do want to make sure we get through this really, really important piece. We at least want to see this piece right here. This piece has to be done today before we leave, okay? So I'm going to sit myself in the unit circle. So therefore, I know that this distance right here is 1. And I know that this distance right here is 1. I'm also going to call this h right here. So my angle, instead of referring to it as theta, my angle I'm referring to as h just because h is my variable. Everybody okay with the setup so far? Okay, now we've got a couple more things we're going to do here. And so these pieces you want to add in. We are going to add in a segment there and a segment straight down. Everybody got that? And we are going to add in angle A or point A. Excuse me. We're going to call this point E right there. We're going to call this point B down here. We're going to call this point C over there. And I'm now going to make one last amendment to my drawing. I'm going to make another triangle. I'm going to extend up and catch that part for even a bigger triangle. And now the drawing is complete.
Do we label that other point at all?
Yeah, we'll call that D. Thank you.
Add another line to make it a bigger triangle.
What's that? What's the biggest shape up here in terms of area?
ACD.
ACD. Everybody agree triangle ACD is the biggest? Okay, so what we're going to do is we're going to represent, there's three different areas we want to represent here. And one of them that we want to represent is that one you guys just spoke of, which is ACD. That happens to be the largest one. So triangle ACD is the biggest. Okay? Triangle ACD is the biggest. Lots of other shapes that we could refer to, but I want to refer to another shape. And I'm going to refer to triangle ACE. Everybody see ACE right here? We're gonna say that that's the smallest triangle, or smallest area, excuse me. And so we have triangle ACE, that's the smallest. And then we're going to put one in the middle of that, and it's not a triangle, it's actually a sector. So it's important you notice this. Everybody see the difference between the triangle and the sector? Everybody agree the sector is bigger than the triangle? So we're going to call that sector ACE. Okay, well, it would be nice to have formulas for area, wouldn't it? Okay, so let's calculate. Can everybody see where this is going? I have an inequality. Do you see how we're going to use the sandwich theorem here eventually? Yeah, we're going to use the sandwich theorem here. This is how this is set up. The foresight on the person who developed this is really incredible. But triangle area is 1/2 times base times height. And this triangle is, again, 1/2 times base times height. And then the area of a sector, if you remember from our time in trigonometry, it's 1/2 times theta times the radius squared. Those are our three areas that we could talk about, okay? Okay. Everybody good? All right. So let's talk about this first triangle right here, ACE. We got to come up with area of ACE. ACE, okay? So I've got 1/2 times the base times the height. What is the base length? 1. So I just ended up with 1/2 times 1 times, and then I need the height. Everybody agree that this segment right here is the height? Okay, so that's my height. I don't have a label on it right now. But notice that this is the opposite, isn't it?
Yeah.
And I'm also given the hypotenuse, aren't I? Which trig function has to do with the opposite and the hypotenuse? Sine. So I could say that the sine of angle H is equal to that opposite side right there, OPP, divided by 1. So wait a minute. If sine of H is equal to the opposite over 1, does that mean the opposite side is equal to the sine of H? What's opposite divided by 1? Opposite. So opposite equals sine of H, right? So this side right here, this height is sine of H. So you have the height. The height is called sine of H. So I've represented that right here, sine of H. I'll be able to scroll up here in a second. We're almost done with the drawing. Let's go to the middle one. We have, so I got less than 1/2. Now I got r squared. What is the radius of this sector? 1. What do you get if you square 1?
1.
Times theta. What is theta? h. So we got 1/2 times 1 times h. Hey, that worked out pretty cool, didn't it? Cool. ACD. Okay, so we've got 1/2 times what's the length of the base of ACD? The base is 1, and now I'm going to need that height over here, aren't I? I'm going to need that height. Let's just think about it. I've got the angle, I've got the adjacent, and I'm looking for the opposite. Which trig function has to do with the adjacent and the opposite? Tangent. So I know that the tangent of angle H is equal to the opposite, which is what I want, divided by the adjacent, which is 1. So what is that opposite side then equal to? Tangent of H. So this side over here is tangent of H. That's our height. Sweet. Okay. Everybody good with the picture?
Yeah.
Now we can focus on the inequality. Let's leave the picture go. Focus on the inequality. Again, what we're trying to do here is we're trying to figure out what one of these two are, and we have to use this picture and this squeeze theorem in order to figure it out. I'd like to get rid of the fractions. What do you want to do? Multiply through by 2. And I get sine of H is less than H, which is less than tangent. Right? Everybody okay with that? Oh, you're almost there. I mean, we don't have much further to go. It's all going to come to just this really beautiful piece here in a second, okay? Now, I want to come up with sine of H over H. Everybody say, I want a sine of H over H. Yes.
Wait, so if you multiply by 2, how come it is 2 sine?
Because 1/2 times 2 is 1.
Oh, it's just 1.
Yep. But the limit that we want is sine of H over H, right? So you kind of got a couple options. I could divide through by H and I'd have a sine of H over there, wouldn't I? But I really want my sine of H over H to sit in the middle because we want to use the squeeze theorem. So I'm going to actually divide through by sine of H. Okay, what's sine of H divided by sine of H? 1, which is less than H over sine of H, which is less than, tangent divided by sine. Ugh. Anybody?
1 over cosine.
Yeah, how'd you get that? How'd you get it?
Sine's on top, so just multiply it on bottom.
Yeah, so sine of H over cosine of H divided by sine of H over 1. Notice when he multiplies by the reciprocal, he gets 1 over cosine, right? Which is secant. Wait a minute, we don't want sine of H, or we don't want H over sine of H, we want sine of H over H. That's what we want, don't we? So I'm going to take the reciprocal. And when you take the reciprocal, things change. Think about this for a second. What's bigger, 4 or 3?
4.
4. We're going to flip those upside down. What's bigger, 1/4 or 1/3? 1/3. When you take reciprocals, you need to switch the signs of inequalities. So what we have here is reciprocal 1 is 1. Greater than reciprocal of sine of H over H, or H over sine of H is sine of H over H. Greater than, what's the reciprocal of secant? Cosine. Hey, wait a minute.
Wait, why did we flip them?
Because we wanted the sine of H on top.
Oh, okay.
I'm going to let the limit as H goes to 0 right now go into effect. The limit of 1 is just 1. What is the cosine of 0? 1. Do you guys remember why? I want to show you. If you don't remember on the unit circle, 0 sits right there. It's the coordinate 1, 0 is cosine the x value or the y value. Cosine is the x value, so the cosine of 0 is 1. So sine of H sits somewhere, sine of H over H sits somewhere between 1 and 1. So what must it be? It is 1.
Greater than or less than itself.
We would say greater than or equal to. Greater than or equal to. I missed the equal sign on that.
All of them?
Yep, sorry. So as you come back, you don't have to go back and redo it all, okay? So we know this one right here. This one is 1. By the sandwich theorem and that crazy drawing and all that, we've showed that the sine of h over h, limit as h goes to 0, is 1. This is an extremely important limit. Limits that we have to know. The limit as theta goes to 0 of sine of theta over theta is 1. That is a true statement that we use in this class. You need to commit that guy to memory. It's super, super important. Everybody okay with that one? Okay, the next one is no big deal. You guys are going to be able to do this one almost without any help. We have to do the other limit. The limit is h goes to 0 of, what is our other limit that we're trying to figure out?
Cosine of h minus 1 over h.
Cosine of h minus 1 over h, okay? And notice what happens if you plug in 0, okay? Cosine of 0 is 1, minus 1 is 0, divided by 0. Notice how we get 0 over 0 again? See, that's what we're trying to deal with, and that's part of what calculus is. So we want to figure that out. I don't know how to do the math, so instead I'll do Spanish. So I can multiply by conjugate, which is cosine h plus 1 over cosine of h plus 1. So I get the limit as h goes to 0 of, what's cosine of h minus 1 times cosine of h plus 1? Yeah, cosine squared of h minus 1 over h times cosine of h plus 1. Yeah. Hey, cosine squared minus 1. Isn't that something? What is that?
Sine.
It's not sine squared, it's I'll write it out. We don't see it. That's okay. Sine squared of x plus cosine squared of x is equal to 1. So we want to come up with cosine squared minus 1. So I'll subtract the sine squared over, and I'll subtract the 1 over. I get cosine squared of x minus 1 is equal to negative sine squared. See, everybody, how we get negative sine squared? Are we okay with that? Okay, so let's put that in the top. So we get the limit as h goes to 0, you're almost there, negative sine squared of h over h times cosine of h plus 1. And we have one last piece here, and you've got it. That's the limit as h goes to 0. I'm going to do just a small little tricky thing here. I've got a negative sine squared. I'm going to take one of those signs. I'm going to take sine of h and place it there. I'm going to place it over the h here. Times what remains in the top? Negative sine. And what remains in the bottom? What is the limit as h goes to 0 of sine of h over h? Everybody see that this is 1? Times, now I'll plug 0 into the second. What is sine of 0? 0. And if you plug 0 into the bottom, cosine of 0 is plus 1 is. So you get 1 times 0 over 2. What is 1 times 0 over 2? 0. So your second limit is the limit as theta goes to 0 of cosine of theta minus 1 over theta. So that's our second limit that we wanted to talk about that we're trying to show, and we showed that that thing is 0. Okay? So we're going to finish that off by putting it up here. You are one step away from being done.
Oh, that's right. Yeah.
And let the magic happen. This is 0. So what happens to sine? This goes away. What's cosine times 1? Cosine. So therefore, the derivative of sine is Cosine of x. Get back here. Come on. There you are. Derivative of cosine is cosine of x. Done. Proved. And once we do that for one, we never have to do it again for the other trig formulas. They all work out quite nicely from there. You saw the one derivative. It's the sandwich theorem put in use. Good job for you. Tell you what, I'm not going to give you any homework for the weekend, okay? But I will say, come next week, Monday, Tuesday, and Wednesday, ready to work. Okay? We got some serious work to do. So, good job.